Today, we are going to talk about monadic operations in C++ because quite few of such things are available now in the standard library, and in some third-party libraries as well. Somewhere the implementations are much better, but we are going to talk about it slightly later. So first of all, regarding myself, Vitaly name. I've been doing C++ development for quite a while. Last years, it's mostly tools, libraries, SDKs, and stuff like that. But I also have experience with different kind of software, for example, for visual effects production or large-scale desktop apps. Now I'm working here in Zivit as a senior software engineer at SDK team. As Anush mentioned, we are doing software or SDK for 3D cameras or 3D scanners. Call it whatever you like. And yeah, that's me. For today, there is like a story behind this talk. This summer or something, I was given a talk at NDC Tech Town, and I was talking about error handling and so on, and briefly mentioned some functional stuff and pattern matching and so on, and asked the audience, how many of you have ever used something of this? And they were like 2 or 3 hands in the entire audience in the first track. And I was like surprised because these tools are handy. And with this talk, I hope to fill this gap, to like share what I think about it. And before we start, we need to understand or define what monadic operations are, because this term is quite vague. Then, yes, then we can talk about like motivation, why we might want to use it or don't want to use it. Then there are 2 classes of standard libraries, stood optional and stood expected. The first one supports some monadic operations. The second one does not support so far, but there are proposal implementation with, well, I would say all regular monadic operations, and we'll talk about this. And by the end, I will show you how to do side effect-less logging with writer monad. But in this talk, we are not going to define monads, semigroups, monoids, and stuff like that. Yes. So we are going to talk about monadic operations specifically. No mass, no shit like that. So, and at a glance, or a definition from either CPP reference, or I'm not sure about the standard because I haven't looked into recent drafts yet, but basically we need to have some monadic-like type that very thin wrapper over some value or something, and it provides some interfaces where you can chain like your computations together in a natural manner. So say do one thing first, then apply another stuff, another, like building a pipeline of operations, very natural way. But again, it's still not clear. That's why we will do our simplest monadic type with simplest operations to illustrate this. Here I have type. Sorry for this, but it's struct and template and whatnot, called and then. And with this type, you can wrap whatever value of type t here, and then, come on, it's broken.
Technology, yay!
Yeah, sorry, go back. Yeah, for some reasons it got broken, but it used to work. Anyway, then we have 2 operations, and those operations and then, they basically accept a function f and invoke it on the value this thin wrapper holds. There are 2 kind of operations. You can see, okay, I can do it once more again. There is like ampersand by the end, and there are like double ampersands by the end of this one. Oh, it works now. So, and it means that this function will be called like on the second one on temporary object, from which we can simply steal or move value. And this is super important. I will omit this second signature for all other examples, but please expect this is here, because when you do this kind of chaining, having this stuff you can call on a temporary object is super important. And below there are also like two helper stuff, the thing to create. And you can also notice that here we remove a const volatile ref from the type to store it like just a value. And then there is a helper make composable that wraps whatever into this monadic wrapper. And that's basically it. These are monadic operations like and then you can chain, and they are consistent. They also should return monadic type as well. And this type, like stood optional, stood expected, are called monadic. But let's see, we have more examples how to use this. There is a task, quite common task. We have a sequence of numbers, say integers. Then we want to transform it to a sequence of strings, and then we want to join it through, say, spaces and hyphens. If you probably know this is common like map reduce pattern, so we apply some functions over all elements of collections, and then join it all together. And then we also want to display the result. I have some functions here to do this, to use in this monadic operation. Since we do not have like map on vector, for now at least, there is a function that transforms all elements of vector to strings. And please notice how this function is implemented. It accepts vector, or if it's like a regular map function, it would accept one element of vector, but it returns this make composable stuff. So then after this function, we can continue chaining stuff. We can continue compose our operations, right? We have second function that just implementation is not super important, but this function join that can join vector of strings with like we can assume for simplicity that it's not empty vector through hyphen and space. And I also have a function to print everything. But please notice, and this is important, that this function just prints. It doesn't return anything. And this kind of doesn't fit the pure concept of monadic operation we have as standard. And it means that such functions you cannot use, say, with stood optional and so on, because they're inconsistent. They do not return the same or similar monadic type. All right. How do we use it? That's a naive usage example. As you might see, we just wrap in a vector of 1, 2, and 3 into something. Then we apply toString function. Then we do join, and then we print in. And as I mentioned before, this one is kind of not really, well, pure stuff you should use. And the canonical or recommended way by standard is this one. So you have like your result, and this result is also kind of a monadic type that's wrapped in our and then. And after that, if you need to print or do something or extract result or manipulate somehow else, like non-monadic way, if we can call it this way, then we should dereference this type. There is like small star operator here. It wasn't in implementation. It's again broken. I shouldn't use this stuff. But yeah. That's the way how it should be used. But say, does this look familiar to you? Yeah, for some does. So that's what we got, I guess, in the previous standard, C++ 17. We got ranges, or ranges v3. And those library also provides monadic operations for us. And instead of like dot or make composable, we have pipe operator here. And pipe operator simply wraps something like, say, a sequence or a range. It's a separate object. And then you can apply operations. And those operations are lazy. And until the last line, when we convert everything to string, like ranges column to string, to stood string, the calculations are not happening. And I don't want to like focus too much on this slide because it's not a topic. But here, specifically, I used ranges -v3 because unfortunately the standard library, well, is lagging behind as usual and doesn't provide all of nice things. For example, join function, as far as I remember, yeah, does not accept a separator. Probably I'm mistaken. It does? Okay.
No, oh dear.
Yeah. So, but please, if you want like to use it for your experiments, try to consider ranges v3. It's quite easy to add to your project. It's available for both Con and VC package. It's header on the library. Feel free to use. You don't need to reinvent a wheel and use like all machinery I put as an example, like and then, because it's already here in the library. So now we can probably better define monadic operations for C++, and it's like probably any function object from some value to composable something, or from composable to composable. That should be monadic operations for C++. And if it matches this, probably like at least one of these laws, we can consider it as a monadic. After all, no other laws like are checked during compile time, nor guaranteed. Basically, all functions you supply to this function, they should satisfy one of those two stuff. And it's either returns composable something like another state optional or another state expected, or it's like wrapped for you, quite, I would say, implicitly. Any questions so far? You can shoot, by the way, if you want during talk.
Would you consider future as a monadic type?
The question was about std_future, whether this is like can be considered as a monadic type or not, and I wouldn't name it monadic type, to be honest. Yeah, because of like many things, it's not necessary that std_future like returns something on which you can chain, on which you compose your operations and computations. You need to like probably wait or take a promise or pass it somewhere. But for C++,
maybe std_future isn't. I mean, we've got some futures in Qt that that are doing something like this. I don't know them very well, but it's a future in principle is a thing that you can do with an operation. It's just that, well, that's a future as a result of the and then operation.
Yeah. Yes, I agree. In some languages, like for example,
so future hasn't really lived up to that idea.
Yes.
In principle, a future could be an.
Yes. It could be for Qt futures, and it could be for some futures or promises from JavaScript world, say. So that would probably match this definition. But again, it's like kind of very weak, and it's not probably even officially defined. Here we just, well, to be on the same wavelength, so we are talking about the same things. So it's, yes, not like strict stuff. But now, that's a question you might ask yourself, right? Do you really want to try using such operations object or not? And as usual, there are some pros and some cons. Let's start with positive things. And if you start using this, even from our first example, you can see that you gain this tiny reusable set of functions that you compose all together. They have typically meaningful names. They can be reused. That reducing boilerplate code, I'll show you how in the next slide without this if else, and there's a check-in. Arguably, it provides like more or less clean control flow when you're doing like your computations more natural way, rather than wrap, like say, power of something, like the set of nested functions that you're doing just then. It's slightly probably better. And hopefully, those operations do not have any side effects. Like throwing, writing, it's again up to implementers, but yet it's probably nice to keep them as clean as possible. So, and there are cons, and cons mostly in terms of C++, I would say, because there might be some performance penalties. Not always, but there might be something, so some overhead. And if the implementation use some type erasure techniques or something like that, there might be extra dynamic allocations. So not always, not for the standard library, but for some third-party libraries, that could be. And like another cons, it's not on the slide, but might be hard to get used to it, to do this chaining instead of like classical calls of function, this procedural style. Arguably, yes, I agree. That's why it's not a cons of monadic operations, right? So, since we now have terminology, we now can understand whether want to give it a try. Now, let's talk a bit about optional value, or stud : optional. What this? This is basically a type that holds either value or nothing, or no value. According to the standard and documentation, there are no extra allocations. It just no dynamic allocation. It just feeds the stud optional structure. It's easily convertible to bool. There are both probably explicit bool operator, and there is like methods to check whether the value or not. It can be cons export, which is cool. So you can use it in compile time, if you will. And from the upcoming standard, from C++23, it supports some monadic operations, at least 4 major operations. The possible and very naive implementation could look like this. And here we have either value or has value. I checked in GCC standard library implementation, it's pretty much this way, but there are a lot of checks, a lot of optimizations, and so on based on types, but it looks this way. And there is one function called an _then, and as you can see, it already contains some check. If this type has value, if there is a value, holds value, it invokes a function you provide for this operation, and if not, that just returns some null opt, which is a structure that shows that the optional thing is empty. And it also allows you to avoid some explicit ifs in your code. Yep. So now the real example. We have one of the most complicated functions, but I use this only because we can have simple condition here. It's a function to divide two numbers. And say we don't care about context now, why it fails. So if we cannot, like, denominator is 0, we cannot divide, we return stud null opt. Or if it is a value, we return something. And please see that it returns stud optional, not just a double. And we also, when we return, we also wrap it into stud optional. So it was like very similar machinery that I show you in the beginning, like make composable or pipe operator or something. We need to wrap type. And below, there is a usage example. So we just check in whether this is something. And if there's something, we print this is something. If there is nothing, we just don't print. For printing here and further, I will be using this FMT library, which is nice, and also supports some compile time checking for arguments count, so on. So I would recommend to give it a try as well, if you want. At least we use it. And yeah, but now, if we want to have, the previous example wasn't monadic enough. Now we have more operations. Some of them might fail. We have square root here, we have power 3, we have something to convert value to string. They're probably not really seen, but value to stir, it's like underscopes to stir. And to error, it's also underscopes here. It's like not 3 different words, right? Now we want to compose it all together. I guess we don't need to even read it because the names are quite descriptive. So what we have here, we have something, some result. We can divide two values. Then we can extract square root. Then we can do power of 3. Then we can transform. And if it fails, some operation fails, we can convert whatever to the error, return an error. And then we can print a result. And below, there are 3 cases. The first one is more or less fine. We have 2 and 4. And by the end, we are getting 2.8 point something. There will be more numbers, I believe. And for negative square root, will fail. We don't support like any complex numbers or whatever it's called here. And division by 0 is also fail. So we have invalid operations. The difference between and then and transform is mostly like, I would say, semantics, that how you want to highlight the meaning of what you're doing. Because and then function, it's very close to flat map from functional languages. It just return another composable type. So if we go to the previous slide, you may see that square root returns like optional type. That power 3 returns optional type. But value to string, that returns just a string. And this method transform, it's like a map from more functional languages. It will wrap it to optional type for you. So you don't have to return it like yourself. That's the main difference. And if you say want to show that, okay, this operation is a transformation on my value, I want to map it from something to something else. Okay, fine, I use this one, and I want this machinery to wrap it for me. But if I want to like do completely other operations, like another action, say, so I use and then and return my monadic type from it.
So I would imagine that transform is what you want to use when this operation always works, and then is what you want to use when it might not. So
yeah.
Really, POW3 ought to be a transform, and Squirrel is naturally an and then because it has to be.
Yeah, that's true. That's for sure as well. There was a comment and transform we can use like if this operation will probably never fail, at least explicitly, and then we can use if this operation might fail. It's also a fair point, yeah, thank you, Ilya. So with that, we can move to the review of monadic API that provided by studoptional, and we have like only 3 functions there. We have and then that just invoke this function from t something to optional v. And by the way, see that you can also change the type of the value of the wrapped value. It might be like optional of say string, not of double. So it might be different types. And transforms, it just transforms from t to v from some type to another type. And or else it's just an error handler.
Why does it take an input of type t?
It's not it.
What does f take an input of type t?
It's what it's about f function. It's not about transform function. Transform take f and f is function. Or
go back to your actual function past or else.
Or else there is probably mistake on slide, but or else doesn't take any types because because so it does take any types at the last bullet. Here lies tiny bullet. Yeah, this error handler that doesn't take anything, it just will be invoked on error. And if you need to do something else with probable error or return some optional, you can use and then function that accepts like the value. So that question also might appear. When should I use this stud optional stuff? And well, naturally you can use it when you have this chain or pipeable computation and some operations might fail and you don't care about the context at all. So just, okay, something is failed, we can restore or we can return this failure message and we are fine. So it says either value or not values. And there are like 3 cases I have here, quite common cases I would say. The first one is stud optional of stud string. Should we use it or shouldn't we use it? It's very questionable. It's up to, well, to implementers and the situation. For stud string, like empty string, can already identify that there is nothing.
Sometimes you want to distinguish between an empty string and no.
Yes, that's why it's questionable. And yeah, so you can do that, but yeah, or you cannot do that. And for some libraries, say for Qt, right, there is, I would say, I already forgot it, right? But the null string, yeah.
You
so
wouldn't forget about that. You'd stay forgotten, right?
Yeah, all right, good. Yeah, but there are some things basically that, yeah, can serve as well as a trait of no values. The second small bullet is like stud optional of a pointer. Well, it might not be a good idea, right? Because if there is like null pointer, it's already null pointer, it's already nothing. So, and you probably don't really want to, well, to wrap it into stud optional, unless you want to do chaining on it somehow. And the last stuff, it's just a regular use case. So if expression is correct, we are doing make optional, and if it's like not correct, we return in stud null opt. It's regular use cases, I believe. But what if I do care about context? If operation failed, I want to know which operation in my chain failed, and I want to like do something with it. And we also have machinery for this. In different languages, it's called different way. It's like result in Rust, it's expected in C++, and it's either in like many other languages. So, but we should start with what it like replaces this I would say either monad or expected type. And here, if you want to pass some context of error, we typically use exceptions. And this is what is recommended by C++ core guidelines. You need to propagate something on top, use exceptions. So you will be good. Nah, there are many, yeah, I know. Qt developers, probably embedded developers, and some other guys. Yeah, I know. But anyway, it's a recommended way. Don't judge, please. It's not my invention. So, but anyway, here we have absolutely the same functions. But in case if there is error, it just throws something with invalid argument. Then this creates exceptional event, handed it over to runtime system, and so on until it reaches first handler. And it's a regular machinery. I guess all of us worked with exceptions, like at some degree, so we don't need to spend a lot of time on it. How to use it? We just have regular procedural style. Then we invoke in our computation functions, and if something goes wrong, we just catching it and printing. Looks good so far. Not really, but okay. But to avoid these exceptions, these side effects, and so on, there is exception type, or expected type, sorry. And this is basically a target union with either t, which is a value, or error e. There will be no dynamic allocations. The type is convertible to bool. It supports monadic operations in original proposal, but unfortunately they were not accepted for C++ standard libraries so far. That's the reason why we will be using the implementation by Cybrand, which is like a namespace in TL expected by his nickname. So, and yeah, all expected things in our examples will be prefixed not stud. But it's easily available for experiments, at least in VC package. I haven't checked with Conan, so just fine. Traditionally, there is naive implementation. My naive implementation of stud expected, it just inherits variant, uses its constructors. There are two methods to get either an error or to see whether this is a value, and the operator bool to check whether it contains value or error. But just don't put too much attention on it. So, example, with TL column expected. We have absolutely the same or super close code structure as we had with exceptions before. But what I want to do is create a type op or operation result, and this TL expected of double and string. Double will be for values and string for errors. And as you may notice, all functions also return this operation result. So if, say, the denominator is 0, we return in something unexpected. There is helpers or additional machinery to wrap it to make it unexpected. If not, we divide. The same for square root, and power of 3 is just power of 3. We assume it can never fail. So the structure of code is very close. And in C++, we do not have like any, I would say, fancy syntactic sugar or part of language. Like say in Rust, there is like operator question mark to unwrap it and whatnot. We have to do like ifs and chains. But how do you use it? Absolutely the same as it was with std optional. To be honest, we have divide, and then, and then, and then. So if there is a result, or result has value, you can use both. You can use the value, and if it's invalid, it's invalid. But yeah, again, if you need to add like more handlers or something like that, you can also transform this stuff to the string and then return string, but it's probably not what you expected, right? Because you expected to have like a value, double value, and yeah, if you need an error, you can do it this way. Check it after that. So there are APIs again. And now here with tail expected, we actually have map function, but since there are like two alternatives possible, value or error, there is like map function for value and map function for error. And then also for, like it works absolutely the same, it's like a flat map. And or else function here, it's not a mistake, because this or else function, according to implementation, it actually accepts a value. There might be error might be passed to this function already, because there is some context and there are two alternatives. Yeah. But now you might have another question. So when should you use this std expected? And the natural way is an alternative for exceptions. You don't like exceptions? Return std expected. You again want to chain or pipe in your computations, and you want to share like additional context. So where failed, what failed, why it failed, and so on. That's 3 use cases for this. And we are good on time. So now we learned how to handle like these exceptional situations, how to chain our operations, and it's time for logging with monads. So how can we do side effectless logging? And I have one more example. The best example, recursive factorial. Don't do that. Probably these particular things can be calculated during compile time if there are no like dynamic memory allocations and so on. But anyway, we have function, we have simple factorial. And all of a sudden, we want to trace execution of this function. We want to add some, say, loggings. So what's happening on each iteration? How can we do that? The example is just below. For logging, SPD log used here. So log something, debug logging, it's not important. And we just log in each and every computation on each step. So for factorial of 0 is 1, and that would be similar things will be logged on each step, like 1, say for 1, 2 for 2, and so on, like 6 for 3, and so on and so forth. But this, it's not good. So what's wrong with this logging? And in particular, there are side effects. A lot of side effects is happening. And because of those side effects, it's hard to compose and it's hard to test, because the side effects even can appear with a dependence of release and debug builds, right, with this logging. So it might log something in debug or not log something in release, or SPD log debug probably even uses like ring buffer. So many things can be happening. We're using basically global object inside of our function. Whatever can happen. And this function is not referential transparent. It means that we cannot replace it with the computation result of this function, say factorial of 5, 120. We cannot put 120 to each places of call of this function of factorial 5 with keeping the same behavior of the program. So that's also bad. It's also reduced predictability of say, our program. And now we have very nice abstraction. And as you may notice, for like all these monadic types, so it's like very, very thin wrappers over 1 or 2 values. Here we have a struct writer. We have log type, as a first field and value type as a second field. And it's basically a combination of those two types with handy methods like map, flat map, or tell and swap. Map and flat map you're already familiar with, and tell is just extracting login, and all of those functions, they return another writer. They are not altering the current one. So it makes like this immutable state. But how can we use it? Because it's very interesting use cases here. Before we start using this writer, we'll define a few types for it. And the first type will be used for logs, which is a simply vector or another type. You can put whatever you like here, another ring buffer, whatever you want. Then we have value. In our examples, value will be integer, and logger, this name of our writer, quite common naming convention. Don't touch here. It's So it's like writer of log and value. Prefix fl, it's where I put my teeny tiny library with all of these concepts. It's not published yet, but I was just experimenting. So, some examples. Say we have a logger of an empty log and one value, and then we want to transform the value inside. We use a map function, and to the L, the value will be 2. Now we want to transform it to say something else, to string. We can map it to string easily, so that will be stud string now. Then we have a flat map, and flat map should return another logger, and it allows to do some manipulations with the value contained by logger. And also proper flat map flattens contents. So this implementation doesn't, but we are not going to talk about it. So as a result, you will get a log of 2 entities. Please notice it of foo and bar, and the value will be 2. We will talk about it later, how this is probably the best feature of this writer monad, that it allows you to quite implicitly compose in logs. So you just do either tell or add in another logs, and it will compose this for you this way. The last example, so we tell foo, tell bar, tell bus, and again, and it's all composed as a single vector of strings, which is very cool. And if we have obviously different underlying type, if our loggers say we're a set, there will be no duplication for the last example. But we have a vector, and there are 2 the same strings. But how this is happening? And at least in many implementations I've seen, there is one more helper class with only one method called combine. And this combine methods, probably matches only one law. This combine operation should be associative. So if you say A combine B combine C, it's no matter where you put parentheses. So you can combine A with B first and then with C, or say B with C and then with A. So it should match this thing. And I have a specialization here for, I have it for stud string, but I could have the same for stud vector or for stud set or for whatever, for many containers. And it simply combines, say, 2 strings or 2 elements, and then method tell implemented as this way. And here is very simple implementation without all of the checks, without concepts and stuff. We are not checking whether semigroup exists or whether it's possible to apply something or what's returned. So just this implementation. That's how tell implemented, and a very similar manner flat map is implemented. Yeah. No. A semigroup, it's probably another monoid has an identity, right? Operation is the next one, and semigroup shouldn't have. But anyway, we can talk about it later. But
algebra, not whatever the computer scientists puts in.
Yeah. Right. But anyway, for say if we want to implement the operation called reset, we need to identity, and we need to use another helper for this, but it would be problematic. But yeah, not the point. So how can we improve our logging now? That would be very first iteration, and that's how many people, and myself as well, because I'm familiar with function stuff, could implement it. So we doing pretty much the same as it was before, but now we are not logging, only returning logger or adjusting logger. So the alternative branch else, factorial now returns logger, and we can just decompose it to logger and value, calculate some answer, then manually adjust logger, and then return logger with adjusted things and the answer. This looks already better than it was before, because there are no side effects so far. But the question is, OK, you can show that it works, right? So, and how it works. This factorial of 5, and log contains all of these 6 entries, and result contains 120. But could we do it, say, better? Can we utilize all of these monadic operations, computations we learned so far? Because that might help us to write more compact code in general. Yes, we can do it slightly better with this implementation. So we're still returning logger for the default case, but now we are using map function, because we can chain now a little bit. And even if it stores it to object R, I just did it to fit it on slide, but we can just chain it. We can return factorial tell for teller. So, and the last I telling, we just put in another log entity to the result vector. And using this semigroup stuff, it all will be combined. And new entity will be added to the logger.
You can't actually chain it back again.
Yeah.
Because you need it to reference R from inside the parameter list of tell.
This
so
is,
you didn't need to set it local variable.
Oh yeah, probably that's true. Yes, we cannot do it. But with my second example, we can do it. So, but can we do it like purely functional way? And yeah, we can do that. First of all, we need to extract more functions. We need to extract log entry function. That will be just, say, return log entry, and it returns vector of string, not just a string, because of the type of our writer. We need to combine, we need to have the same type. Now we have two functions. We have functions for multiplication and function for log entry. They extracted here like lambdas because of the capturing I, and we can extract it as a free function from factorial in general, and just do some carrying. If our function return another function, that we can avoid these capturings, right? But it would just make code slightly harder, and we are not going to. And the last line, we are utilizing the fact that we actually have if-else that is an expression that returns result. It is famous ternary operator. And what we do here, we have like logger, empty logger for 0 case, and then factorial calculated for other case. And we simply do flat map on log entry. And yeah, that's done. We have like almost one-liner for our factorial, which is...
You could have just used I instead of the ampersand sometimes with square brackets as well. But anyway.
Yes. This was a comment about improvements in syntax, but yeah, that's good. Yes, we can use it. Yeah, for sure. So...
Logger should have a double G. But anyway.
Thank you. Yeah. And with that might be slightly advanced stuff, or probably harder to understand, but that's how we can get the same one-liner as we get for regular factorial, but with additional logging stuff if we want to log on every iteration. And this is completely side effect-less, and looks arguably nice. Now we can do some brief review of the API. We have map function that transforms the value writer holds. We have flat map that also transforms value but returns another writer, and logs in this case will be combined. Then we have tell, and this just to add some more entities to the log. But there might be another question, though. When you should use writer? And you should use it, obviously, for logging without side effects, but there might be some penalties, right? Because we are moving this vector of strings or whatever type around, and if, say, it's like non-movable but only copyable type, there might be some penalties for copying extra object, for allocating extra things, and so on. But arguably, if you need logging, and if you have performance critical system, other loggers might also don't behave well, but...
I mean, as long as you use your logger and you pass in a logging type, which in fact produces a side effect instead of storing it in memory,
yeah,
you don't actually have the, okay, you have got the side effect, but now you've solved the performance problems, shoving out the I/O port.
Yeah.
So, it gives you the compromise that
yeah,
in your test,
yeah,
collect up the output instead of outputting it.
Yeah.
And in your production code, you get it both ways.
Yeah, sure. There was a comment for recording about compromises. So we should keep balance when we're doing things in development always. Yeah, and with that, but there is another interesting question before we finish. So, should you really use writers? Because there are, and other monads as well, because there are some downside, and it can easily bloat your code base with many nested expressions. Just imagine, I used very simple example where the value is a type of a double or int or whatever it was. But if we have something more complicated, like we want to say carry some states, errors, set in some context and whatnot, that might be more complicated type, like either or results. And then, if you have it, you can get this infinite ladder of callbacks, right? Like this way. And it completely bloat your code. There are tools in functional programming world that can help you with that, like these transformers for comprehensions. It's basically flat map. But in C++, we do not have something like that. So my point is, use it, please, but use it with care. So don't just let it bloat your code. If you have some probably tiny things or some computations that you can pipe, well, do it this neat and nice way. But if you trying to write the entire program or big app or a library in this style, that might be complicated internally. Yeah, and we have 10 minutes, I guess, for questions. Thank you.